Hello everybody, my name is Marian Villa, I'm Senior Full Stack Product Designer at Node.js. I also want to introduce my colleague Santiago Gimeno, Senior Software Architect at Node.js. As you already probably know, we work in observability, focusing exclusively in the Node.js runtime. But today we're going to discuss only what's available in the open source space to implement observability in your applications. Today we're going to present line trains, instrument your Node.js applications with open source software. And before starting our presentation, it's important that we keep in mind a few of the main concepts of observability. It is important to understand that when we talk about observability, we need to understand what questions we seek to answer or clarify when detailing a system. The first questions we undoubtedly ask ourselves is why my application have a certain behavior, and to solve this, another question, the first thing we must do is instrument our system so that our application can emit signals, that is traces, metrics, and logs. When we do this in this correct way, we have the necessary information that we needed. But what is observability? So in synthesis, observability is the ability to measure the internal states of a system by examining its outputs. Your system and apps needs proper tooling to collect the appropriate telemetry data to achieve observability. But what is the telemetry data that we need? The three main pillars of observability will be: first, metrics as dots, logs as lines, and traces as traces. When we name our keynote in this way, because with dots, lines, and traces, you have the whole picture of your system, and we want to create a direct reference to the basic core concepts of visual representation in a plain planimetry. But let's jump to dig a little bit more of this concept, not just enunciated them. First, start with metrics. Metrics are aggregations over a period of time of numeric data about your infrastructure or applications. Examples include system error rate, CPU utilization, and request rate for a given service. Briefly, a metric is a measurement about a service captured at runtime. Then jump to our second core concept, logs. A log is a timestamp message emitted by services or other components. They are not necessarily associated with any particular user request or transaction, but when they are, they become more useful. We'll get into this in a little bit later. Before defining what a trace, our third concept is, we should define the concept of a span. A span represents a unit of work or operation. It tracks a specific operation that a request makes, painting a picture of what happened during this time in which that operation was executed. A span is the building block of a trace and is a named time operation representing a piece of the workflow in the distributed system. All traces are composed of spans. That's why the importance of this concept. And before jumping directly into traces, let's talk about context propagation. It's an important functionality that is required to implement distributed tracing. We can define it as a mechanism of storing state and accessing data across the lifespan of a distributed transaction, either across executing context inside a process or across the boundaries of the service that conform our system. For in-process propagation, we will typically use something like async local storage class from the async hooks model. And for across processes, it would depend on the IPC protocol used. As an example, for HTTP, there's the trace context specification from the W3C, which defines the transparent and translate headers to propagate tracing info. Now it's time for the third core concept, traces. A trace records the paths taken by requests made by an application or end user. As they propagate through multi-service architectures like microservices and serverless applications, it is also known as distributed trace. Without tracing, it's challenging to pinpoint the cause of performance problems in a distributed system. We just define the concept of tracing, then this all sounds like very abstract. What does this really mean? What is this good for? Let's see it with a very simple example. With the same architecture we will use in our demo, we can clarify this for you. So let's say that we have a distributed application like the one in the picture, which I said with the application will be demonstrated later. It has 4 Node.js services, API, auth, service 1 and service 2 and one database. Imagine we having intermittent performance issues. They could come from several points, wherever is the database access, network link status, or DNS request latency, etc. Finding where exactly may become a very hard and time-consuming task. The harder, the more complex the system is. Distributed tracing is going to help us a lot with that, as we'll be generating tracing info on every point of the distributed system A, B, C, D, and E. Not only that, with the request goes through all the services, thanks to context propagation, some tracing state is going to pass along so all the tracing info can be linked in a very same request. Also, that info will be exported to a backend service where we can easily visualize and analyze the data, allowing us to identify where the issues may come from. More on this later on the demo, and before that, it's really important to talk about instrumentation. First, instrumentation is the process of adding observability code to your application. We can do it either automatically or manually. With automatic instrumentation, our instrumentation libraries will take the configuration provided through code or environment variables and do most of the work automatically. In the following example, using the OpenTelemetry SDK, we show how we can automatically generate spans of every HTTP transaction handled by the Node.js HTTP core module. Manual instrumentation will require more work on the user-developer side. Enables far more options for customization, from naming various components with OpenTelemetry, for example, spans and the traces, and to adding your own attributes, specific exceptions, handling, and more. See the following example where it shows how to manually generate the span also using the OpenTelemetry SDK. Okay, all about OpenTelemetry sounds good, but how do we correlate data? The way we historically will implement a typical observability pipeline is shown in the following picture. In this case, having all the data at your disposal is great and can give us a valuable overview of our system. But unless we are able to somehow correlate the observability signal, metrics, logs, and traces, we won't be able to have the best of it. OpenTelemetry comes to solve this problem. The solution is going to come from correlate these signals. This can be done by applying the same concept of context propagation that was used for traces to metrics and logs. So that identifiers such as the trace ID and the span ID are associated with those signals. So, for example, for logs, if we can correctly identify which specific request generates the actual log ratio, we will have more useful information to take decisions. But OpenTelemetry is much more. It defines an API, which defines data types and operations for generating and correlating tracing, metrics, and logging data. We have SDK. It provides language-specific implementation of the API. We have OTLP, a protocol to transport the telemetry data. We have a collector to receive, process, and export telemetry data. And finally, we have semantic conventions to have a well-defined naming for the attributes associated to the signals, service name, HTTP port, etc. Next, Santiago will present a demo in which we'll showcase some of these OpenTelemetry features along with other open source tools. Santi, the stage is yours.